Okay, class. Assalamualaikum. Selamat tengah hari. Okay, so this is our new chapter. Okay, it's the cosmology chapter. Okay, so we see what we will learn in this topic. Okay, the first one is the universe on the larger scale. We will see the universe on towards the larger scale, the expanding, how is the expanding universe. Okay, what is cosmos and the geometry of the space. Okay, will the universe expand forever? And dark energy and cosmology, and also the cosmic microwave background. Okay, so those are several questions to be answered here. So how big is the universe? How long has it been around, and how long will it last? What was its origin and what will be its fate? And is the universe one-time event, or does the recurrence and renewal itself in a grand cycle of births, death, the death and the rebirth? Okay, so how and when did the matters, atom, and our galaxy form? So as we can see here, the universe on the larger scale, so we have showing in the structure on every scale. Okay, so to determine these subatomic particles, the atoms, stars, galaxy, and the galaxy cluster. Okay, so the largest scale is when the universe can be regarded as more or less smooth or featureless. Okay, so cosmology is the study of the structure and the evolution of the entire universe as a whole. So that is the general meaning of the cosmology. Okay, so the end of the structure, okay, we have this SDSS, okay, kind of survey or catalog, Sloan Digital Sky Survey, that obtain the redshift data for galaxies to a distance of 1000 megapixel, and it discovered an extended filament 300 megapixel from the Earth. So it's known as the Sloan Great Wall. Okay, so you can see here where is this Sloan Great Wall. So we have this in this distance and the redshift area. So the largest known structure in our galaxy, in our universe, is currently the Hercules Corona Borealis Great Wall, or the Great GRB Wall. Okay, was discovered in 2013. Okay, with these properties, it reached of a supercluster about 50 megapixel across. Okay, and also most walls and the filaments contain. So this structure cover wide areas of the sky and enormous volumes of space, but their size are small and compared to a distance to quasars. So the field of view, they have a narrow field of view, only a small patch of the sky that allows us to study extremely faint and distant galaxies. Okay, so the volume surveyed then become a long, that thin pencil beam that extended deep into a space rather than a wide swath through the local universe. So along the line of sight, cluster and walls show up as a spikes. Okay, as you can see here in the bottom plot, number of galaxy versus the distance. So the spikes in the distant distribution here is separated by the voids. So the spikes is referred to the cluster and the wall, as you can see the arrow here. Okay. So the data from both kind of survey and the Lyman alpha forest in quasar spectra is seen to agree on the size of most large known structure in the local universe. Okay. Okay, so the cosmological principle result the large-scale studies, okay, which strongly suggest the universe is homogeneous. So its main is the same everywhere in any scales range. Okay, so it's homogeneous. And for example, it also appears as isotropic, okay, mean it's the same in all direction on large scale, and we count roughly the same number of galaxies in any page of the sky. So it's mainly to the assumption, okay, because of the homogeneous and isotropic. So they are sufficiently large scale that is known as the cosmological principle. So this principle is consistent with the current observation that imply the laws of physics are the same everywhere. So the cosmological principle implies these two statements about homogeneity and also about isotropic. And this principle is also similar to the Copernican principle, where humans on the Earth or in the solar system are not privileged observers of the universe. Okay, so we have the Olbers paradox that assume our universe is homogeneous, isotropic, and also infinite in spatial extent and unchanging in time. So the universe should be uniformly populated with galaxies. And therefore, when you look up at the night sky, your line of sight must eventually encounter a star, whether near or distant star. So it may fainter and should be increased as the square of the distance. So they are also contributed equally, okay, and because no matter where you look, the sky should be as bright as the surface of a star. So this is known as the Olbers paradox, okay, that name after this astronomer, Heinrich, that popularized the idea in 1823. So since our nights are obviously dark, either the universe is finite in the extent or it evolved over the time. Okay, so this maybe some recap, okay, because of the we have learned about the expanding universe before, so I will just go faster at this part. Okay, we have learned about the Hubble's law before this. So this is just a recap sub yang kita dah belajar lah dekat previous chapter. Okay, also the birth of the universe, but for this time we include the approach by the Olbers paradox, which if we talk about the Olbers paradox, then you have to think or insert the knowledge about what are the two important terms yang kita tahu tadi, which are the about the homogeneity and also the what is the second one? The about the homogeneous, and also about the second one of Albert's is the isotropic. Okay, so we have three. Okay, so this is Hubble's. Okay, so this is just the how the universe is expanding towards the distance and also the speed. Okay. So the second question, where was the Big Bang? So there is no center to the expansion, that since the Big Bang was not explosion, otherwise featureless and empty universe. So instead, the universe, entire universe itself expanded. So although the galaxy have small scale individual random motion on average, they do not move with respect to the fabric of space. So and the portion make up the Hubble flow is really the expansion of the space itself. And at the time of the Big Bang, the entire universe was a point. So there we go. We have this example of how the expansion happened. Okay, the main difficulty is that we see the balloon of a 2D space, okay, expanding into a 3D space. So our 3D universe is not expanding into some 4-dimension universe. Okay, as far as we know, even if it is, it will not be relevant to our theory of the universe. Okay, so the cosmological in the redshift, so redshift is the galaxy that originally thought as a Doppler shift, okay, the consequence of their motion. So the cosmological redshift, however, is a consequence of the changing size of the universe as the photon moves through space and the wavelength expands along the universe. Therefore, the cosmological redshift should not be referred in terms of the recessional velocity. For example, we have the quasar with z equals to 5 means the observed wavelength is 6 times greater than the wavelength at the time of emission. So it means the light was emitted at a time when the universe was just 1/6 of its present size. And since the universe expands with time, redshift is related to the expansion and is used to express the time. So that is the terminology lah, how to understand this expansion. And until late 90s, the most cosmologists believe the gravity would slow down and ultimately reverse the current expansion. If the gravity is the only force affecting large-scale motion in the universe, a rocket launched from a planet has two possible trajectories. First, unbound trajectory, and the second one is bound trajectory. So this is similar with the Hubble's law, okay, as we have learned before. So the Hubble's law is when we have this red curve is referred to the Big Bang due to according to the Hubble's law, and the distance between them will increase forever, or it can increase for a while and then start to decrease. Okay, so this can be answered with the contraction process. So now apparently we have stopped at this present time, okay, at this point. Okay, for critical density, for a rocket of a fixed launch speed, the mass and radius of the planet determine whether or not escape will occur. So its corresponding factor is the density of the cosmos. And also when the high density universe contain enough mass to stop the expansion and cause the collapse, so a low density universe will expand forever. So that is the fate of the cosmos. Okay, and also some with the bulk expansion, it also undergoes the contraction. Okay, and the nearby galaxy will begin to show the blue shift, and both the density and temperature of the universe will start to rise as matter collapse back onto itself. And this process will be berlarutan lah, akan continuously will happen, okay, and thus the expansion until the collapsion and back to their original state. So we have two futures. It's due to the big crunch of term will be used in explaining the galaxy in the two futures. So either it's collide with the increasing frequency, or it's will shrink towards a super dense. So this is a collapse process, okay, from here to and the back to itself condition. And the laws of physics as we presently understand them, they are simply inadequate to describe such the extreme condition. However, for a low density universe whose gravity is too weak to help the present expansion, and it will expand forever. Okay, and this one is the curve for the expansion forever with time. Okay, and this will continue until a time when the observers on Earth will see no galaxy in the sky beyond the local group. So this condition or state will decrease the temperature until the universe reach the big freeze. So it's estimated to keep forming stars for 50 billion years and allowing our galaxy to shine for another trillion years before a possible big freeze state. And therefore it will require be more than just the density to determine the fate of our universe. And then we go to the geometry of space. Okay, due to the Newtonian mechanics and also gravity to make the evolution of the universe easier to be understand. But in reality, as we know, all the argument or discussion in explaining this happen, it's all requires the Einstein general relativity, okay, and the most relevant one. And we recap maybe a bit about this one. Okay, you have learned about the space-time curvature on the Einstein relativity before, so you can read it. Okay, and also the density of the universe and how the cosmic curvature in the homogeneous universe. So we have three type of large scale geometry of space. Okay, positive curvature, zero, and also negative. So this is the K, is referred to the curvature, and the cosmic density parameter. Okay, symbolized by this. So for low density cosmos, they have this value, okay, of cosmic density parameter less than 1 and high is more than 1. Okay, so for a closed universe, so no boundaries and the universe is finite. Okay, so in 2D world, this is just the surface of a sphere where a light beam stored in some direction might eventually traverse the entire universe and return from the opposite direction. Okay, maksudnya dia bila kita, for example, the simple terminology kat sini, bila kita suluhkan, okay, point out satu source of light, bila kita project dia ke depan, dan bila kita nak patah balik tu, dia akan balik kepada opposite direction lah. So dia akan jadi like cyclic dekat sini, macam dekat dalam gambar ni. Okay, so that is the cosmic curvature, that the average density of universe is below the critical value. Okay, so that is the condition where if you have a cosmic apa nama dia tadi, term ni is a cosmic density parameter, dia more than 1, less than 1, or equals to 1. Okay, so for equals to 1, then we can see or we can say it's a flat surface of a universe. So for in flat universe, the geometry of space on large scale is described by Euclidean geometry, named after this mathematician. And the basic axioms of Euclidean geometry is parallel lines never meet when extended to infinity. The angle of any triangle always sum to 180, and the C, circumference of circle, is related to its radius. So Euclidean geometry is a good description of space on the scale less than 1 giga BC, which refer to solar system to Milky Way. Okay, so this is a basic for Riemannian geometry. Okay, there have 4 here. Okay, about the geodesic, a grid circles which pass through the center of sphere, the shortest path of the 2 point through an arc of a grid circle, and the sum of a triangle's angle. So both geometry, Euclidean and Riemannian, are approximately the same, only if we confine ourselves to a small patch on the surface. Okay, so still in the geometry space, then we have a negative curve, which is the hyperbolic, that was first studied by this Russian mathematician. Okay, so this is the name of the geometry, Lobachevskian geometry. Okay, you can read. So there are 2 points. Most of the local universe up to the Milky Way galaxy, and is correctly described by Euclidean geometry. So this is related to the two geometry previous. Okay. Now kita tengok in terms of the density of the universe. So will the universe expand forever? So we should relate with the total mass on the density of the universe to describe this of the expansion. Okay. So although we have quantified the effect of dark matter in galaxy and galaxy cluster, so its distribution on larger scale is not known. And the gravitational lensing suggests it only adds very little to the overall density. So for cosmologists, they agree the overall density of matter, which luminous plus the dark in the universe yield the uh the omega is in this range. That's still not enough to halt the universe current expansion. This is the cosmic expansion. Okay, so local measurement, for example, the average density of nearby galaxy, they contain uncertainties, and especially when projected onto large scale. So we have to rely on the global measurement to indicate the universe overall density more accurately. And this can be done by observing type 1 supernovae. So there are a carbon detonating supernovae which are very bright and have a narrow space in luminosity. So that is for type 1 supernovae. So if the universe is decelerating, the gravity is slowing its expansion. So the object at greater distance should appear to recede the faster than Hubble's law prediction. Okay, for example, if the universe expand constant in time, so the gravitational velocity and distance will be related by the black line. Okay, so when the object is above the black line, is accelerate. Universe is below the black line and is decelerating universe. The distant object should be above the black line. Okay, so Supernova Cosmology Project SCP and High Z Supernova Search Team both independently showed the expansion of the universe is in fact accelerating. And the data showed the galaxy at large distance are receding less rapidly than the Hubble's law would predict. Okay, so this observation is consistent with the gravity-only Big Bang model that described and new physics is required. And also supernova measurement technique should be introduced, and thus the acceleration concluded is real. Okay, so for dark energy, okay, which mysterious cosmic field that causing the universe to accelerate, and this field carries energy which exerts on overall repulsive effect on the universe, and this field called as the dark energy as a negative pressure, and repulsive effect is proportional to the size of the universe. So when so it increases as the universe will expand. Okay, so this is the how the dark energy related to the gravity. Okay, so since the effect of gravity weak, as the universal expansion proceeds, it is possible for gravity to catch up with the dark energy. Okay, so this means it will continue or accelerate the increase, and the expanding will be forever. Okay, so we have cosmological constant here. And this one also have been introduced in the previous chapter. Okay. Okay, so the present value of the repulsive force is comparable to the attractive force of gravity, opposing the further expansion, which was found to be not the case in the early universe and the far future. So this observation suggests that we live at a special time in history and contradicting the Copernican principle. Okay. So this contrasts with the cosmological constant, which is a property of empty space and independent of any matter or a normal energy that space contains. And another alternative is a phantom energy, okay, possesses the negative kinetic energy and cause the accelerating universe to accelerate more, okay, to a big rip. So this phantom energy is usually dismissed, and since it will make the vacuum energy unstable and make the particles with a negative mass. Okay, so Big Bang is a scientific theory, okay, like any other theory, and this theory makes a detailed, testable prediction about the state and the history of the cosmos, but it must be changed or replaced if these predictions are found to be odds with the observation. Okay, so still in the dark energy and cosmological side. So I will continue this slide 48. Okay. Yeah, 48 in the lecture tomorrow. Okay, that's all for today. Thank you.